let's take a look at the relationship between the electrochemical potential of a cell and the free energy of the same voltaic cell. We know that if delta G is negative, it's a spontaneous reaction. We've also seen recently that if electrochemical potential for the cell, E cell, is positive, it's a spontaneous reaction. So we can actually have an equation that relates the two. First, we need to know what N and F stand for. So N is the number of moles of electrons transferred, and F is Faraday's constant. To the nearest whole number, it's 96,485 coulombs, which is a measure of charge per mole of electrons. So here it tells me my moles of electrons transferred times the amount of charge per mole. That gives me my charge. And my charge times my volts gives me my delta G. So let's take a look at the units. A volt is defined as a joule, measure of energy, per coulomb, unit of charge. So if we rearrange that a tiny bit, a joule is a coulomb times a volt. A joule is coulombs, F is coulombs times volts. I'm going to mostly use the 3 significant figure version of Faraday's constant. That's what shows up on the AP test. The other thing we can do is if we know delta G, we can figure out its equilibrium constant. A negative delta G gives us a positive or large equilibrium constant favoring products. A positive delta G gives us an equilibrium constant less than 1 favoring reactants. So now that we have all that background, let's take a look at a problem. This is one of the cells that you did in lab, a copper ion copper cell and a zinc ion cell. We measured the electrochemical potential, and at 298 Kelvin, it is 1.10 volts. So if I'm going to figure out delta G, I'm going to plug it in the equation at the top. So I have a negative sign and 2 electrons transferred because I go from 2 plus to 0 and 0 to 2 plus times Faraday's constant. Times the voltage. So if I multiply those out, a coulomb times a volt is a joule, but that's a huge number to leave in joules, so I'll divide it by 1,000 and call it negative 212 kilojoules per mole reaction. That releases a lot of free energy. That's delta G. That doesn't necessarily mean it releases a lot of heat, but it releases a lot of energy. That's why we can get electric current enough to measure. We can use them for batteries. I'm going to predict that my equilibrium constant is going to be greater than 1. And as I solve for it, I'm going to start by solving for the natural log of K. Mathematically, that's easier than solving for K by itself. So natural log of K is delta G divided by negative RT. That turns out to be 85.7 because it's the negative of a negative. If I take e to the 85.7 power, I get a very large equilibrium constant. Note that for delta G's, you're going to get some very large negative or very large positive numbers with voltaic cells or electrolytic cells. You may end up with a K that is so large that it tells you the calculator says error. If that's the case, then you have to give the answer as e to the power. You might get one that is so small that the calculator tells you 0. In that case, you would say e to the power again. So let's take a look at some examples. This one, we can see transfers 3 electrons, 3 silver ions going to silver metal. This one, we can see transfers 2 electrons. So pause the recording and spend some time using the 2 equations on the previous slide to figure out delta G for each of these 2 reactions. So you got them figured out? Let's take a look at the answers. Positive E cell should give me a negative delta G, and negative E cell should give me a positive delta G. When I try to plug in delta G equals negative RT natural log of K, I get natural log of K is 287. My calculator couldn't handle e to the 287th power, so I'm just going to leave it this way. That essentially means that if I get this thing going, it's going to go until I run out of silver or I run out of aluminum. It will not reach equilibrium for any practical state. This one, because it has a positive delta G, it is non-spontaneous, has a very, very small K, which means if I start this reaction, I'm really not going to see anything happen. So pause the video again and try the next 2. Okay, for the next 2, you had to also figure out how many electrons were transferred. And for this bottom reaction, it's 6 electrons. 2 times aluminum 3 plus, and it goes from 3 plus to 0, so 3 electrons times 2 is 6. 0 to plus 2 is 2 electrons times 3, still 6. This should give me a K less than 1, and this should give me a K greater than 1 and a K less than 1. And again, e to the something is the best we can do. Part of the experiment that you did earlier with voltaic cells is that you saw that there's a concentration difference. So if I have a copper zinc cell, I know copper ions form copper atoms and zinc atoms form zinc ions. So let's take a look at Le Chatelier's principle. And if I keep copper at 1 molar, that's what it is for standard states, but decrease zinc ions to 0.01 molar, I've decreased a product. Le Chatelier's principle indicates that the reaction would shift towards the right. So I should increase my voltage. Use the same thought process to try to figure out the next 2. Ready to take a look? If you need more time, pause the video. In the second case, I'm decreasing reactant. The reaction will shift towards the left, decreasing the voltage. And in the last one, I decrease both product and reactant equally. So there's no net shift in the equilibrium. So Q is the same ratio that it would have been in standard states. So the voltage is what it normally would have been predicted, 1.10 volts. So now here's your chance to try what happens under non-standard conditions. There are two sets of problems. The first one is oxygen and hydrogen ion and bromide ion. So you'll need to find the E cell for the reaction under standard conditions. You'll need your chart. When you're done with that, figure what happens if we decrease the concentration of hydrogen and bromide ions to 0.1 molar. And then the second one, you're also going to calculate the cell voltage under standard states, and then calculate it if you change the hydrogen ion concentration. So pause the video, and when you're finished figuring these out, take a look. Okay, let's take a look at these. It took a little while maybe to find the O2 plus 4H plus, but that's 1.229 volts. The bromine changing to bromide is 1.065, but we flipped it, so we have a net voltage of 0.164. If we decrease this concentration and this concentration, we're decreasing reactants, and each of these is by a factor of 4, so we're really decreasing the denominator of our Q. Decreasing reactants will cause a shift towards the left. Oops. And if we shift left, we're going to produce less voltage. With the second one, zinc was pretty easy to find. That one was oxidized, so we had to switch its number. Hydrogen was reduced. pH4 buffer. You have to think a little bit. Standard state is 1 molar, so pH is 0. If pH is 4, H plus is 1 times 10 to the negative 4th. It's a whole lot smaller. So if I decrease hydrogen ion, I shift to the left and decrease the voltage. And in the last one, if I increase hydrogen to 6 molar, I increase hydrogen, shifting to the right and increasing the voltage. At this point, you should know enough to be able to finish up the homework assignments and the free response. Let me know if you have any questions.